So let me first introduce the speaker. So I'd like to welcome Professor George Efstathiou today. Thank you very much for giving a talk and getting up quite early this morning. So George is a principal investigator on the Planck team. And they measured the cosmic microwave background. It's probably the best, most accurate data set we have in cosmology at the moment. And so today he's going to talk about some work related to that and the cosmological parameters they measured and their possible tension with cosmological parameters measured using different data sets. So I would like to thank George again and ask him to start. So, but before I do, the speaker did say that you can interrupt any time to ask questions. So if you have any questions about the slides or what he's saying, then please do interrupt him. Okay, thank you.
Well, thanks very much. Thank you for the invitation and the opportunity to discuss the Hubble tension with you. Let me start by saying that, the observations and the distance ladder are not my primary research area. So it's been a sort of, what you will hear is basically the results of an obsession and a hobby of looking at this problem, the unusual circumstances of the lockdown gave me an opportunity to look at a number of issues in some detail. Now, the Land Cdn model is now, well established and fits a wide range of data, in particular the cosmic microwave background anisotropies from Planck. But there are a number of tensions with other data sets. So the H0 tension that's the subject of this talk is testing a tension at the level of the background cosmology. There are other tensions that test the theory at the level of perturbations, like the amplitude of the fluctuations measured from weak galaxy lensing surveys. So I'm not going to talk about that. I'm going to talk exclusively about the H0 tension. And the sort of modern version of this emerged, with the first results from the Planck satellite. So what is shown here as a function of time are distance ladder measurements from the Hubble Key project, first results from the SHOES, so that's supernova H0 for the equation of state project. So these are based on Cepheids. Then the Carnegie Cepheid program, and then SHOES again. So these are the direct distance ladder measurements, and then these are in red Hubble constant measurements in the context of the Land Cdn model, measured from the CMB. So first with WMAP, the numbers refer to the years of WMAP data ending with 9 years of WMAP data, and you can see the emerges, sort of hints of a tension. But then the first results from Planck showed quite a large tension. And over the last few years, so that was in 2013, and over the last 5 years, the error bars on the CMB measurement has gone down. This 2013 result was based on half the Planck data, on half the mission. So the error bars from the CMB have gone down, and the error bars from the SHOES measurement has gone down. And so we now have a tension. And so I should say that there was widespread concern within the Planck team when we got this result, that it was clearly discrepant with SHOES. But if that's what the data says, that's what the data says. So we published it. Now, so here's the current state of play. Okay. So the reset SHOES distance ladder measurement gives you an H0 of 74, plus or minus 1.4. The Planck value is about 67.5 in the context of the Land Cdn model, plus or minus 0.58. The discrepancy is 6.6 kilometers per second per megaparsec, which is about 10% of the value of the Hubble constant, or 4.3 sigma. And as Adam Rees emphasizes, this is not a small discrepancy. So there's something going on. Just to go back to this, direct measurements of the Hubble constant have a long and checkered history. And so, one might say that, well, there are systematic errors in the distance ladder measurements. This has been a problem with us since Hubble's first determination of the Hubble constant in 1929. So, we have a 100-year history of problems with the distance ladder. Let's not worry about it. What I'm going to argue, and the sort of main conclusion of this talk, is that this problem, it's very clear where the problem with the distance ladder measurements, if there are problems, where they lie, and that this problem should crack on a short time scale. We don't have to wait 100 years to get accurate measurements from the distance ladder. Okay, so let me show you something about Planck. One could argue that the recent interpretation is that there's new physics. Okay, so physics beyond the Land Cdn model. So this shows the power spectrum, the temperature power spectrum measured by Planck, as published in the 2018 legacy papers. So you'll see the best fit Lambda CDM model. It's an extremely good fit. And then here I've shown the residuals with respect to that best fit. You'll see a number of wiggles, patterns that some people have speculated might be signatures of new physics. There's nothing very significant there. But one of the things that I did with Stephen Grattan after the legacy papers were finished in 2018 was to push the Planck data harder. Okay, and the way that we did this was to increase the amount of sky area that we could reliably subtract dust from. So we were able to do this and get a more powerful likelihood. And the purpose of this project was that there are a number of, with any data set, there are a number of suspicious features that are at the sort of 2.5, 3 sigma level. So if these are statistical fluctuations, you don't need to improve the statistics very much. Okay, to what you would expect is that if you improve the statistics, and you don't need to improve them very much, then these fluctuations will go down in statistical significance. That should be the overwhelming behavior. New 2.5 sigma things will pop up, but the wiggles like this that might catch your eye, those should become less significant. And so that was the aim of the exercise. So this is described in a very long paper. And this is what we get. And you don't have to do any statistical analysis to see that the residuals here, okay, are quieter. So you increase sky area, make a more powerful likelihood, and what you find is that it provides an even better fit to Lambda CDM. So, so our conclusion is that, from the Planck data, there is, Lambda CDM provides a perfect fit to the Planck data. There's no evidence for any deviation, and even hints of of possible deviations from Lambda CDM in the 2018 data become weaker in this analysis. So,
George?
Yeah.
Can I just stop? So I have a question. So what about the low L modes? There is significant, some kind of deviation in the low L modes?
Well, okay, so what you're primarily getting from this analysis is increased sky error at the high frequencies, okay, which reduces the errors up at these high multipolars. Yeah. So things like this, we've got an analysis of are these points, for example, are these points statistically significant? And the answer is no. Okay. What is very difficult to show you graphically here is that we fit a theoretical model, and we also fit for foregrounds. Okay, and the foreground error isn't folded in here. Okay, so I mean these points are not very discrepant anyway, but if you then look at so if you fold in the error in the foreground model, they become even less significant.
Okay, thanks.
All right. So in this shows you the temperature power spectrum, and I mean it's a long story to go through all of this analysis, but it should be obvious without doing any statistical analysis that this spectrum is cleaner. Okay, and the same applies for the polarization spectrum. Okay, so if we look at the grid of models that we analyzed with in the Planck papers, so this shows you the values of H0 for Lambda CDM, then adding a neutrino mass as a parameter, number of relativistic species plus neutrino mass, sterile neutrino curvature, dark NMG, variation of the equation of state, run in the spectral index, etc., etc. You never get values that are close to the Rees, value of around 73 or 74. Okay, and this is actually quite characteristic of most of the proposed theoretical explanations to relieve the Hubble tension, that they tend not to increase the central value very much, but by adding more parameters and introducing more degeneracies, then the error goes up. Okay, if you add in baryon acoustic oscillations, things tighten up, and again, you get stable values. Sorry, can I just stop a second, because my dog is going berserk at the door. Okay, so I just need to sort this out. Okay.
Okay.
Frankly, I'm trying to give the talk, and the dog is scratching the door. Please keep the dog and don't let it scratch the door. Okay? All right, but it's disturbing. Okay. Sorry about that. Okay. So although you see the Hubble tension first emerged really, with the Planck data, it's not really a Planck issue. There are other ways of seeing the Hubble tension. So probably you're familiar with inverse distance ladder type techniques, where you take a characteristic scale, the sound horizon, measured from the CMB. So the Planck value of the sound horizon is 147 megaparsecs, and then the baryon acoustic oscillation data measured from galaxy surveys, which is shown here as these red points. These are the boss points. Then there's a quasar BAO, and then there are Lyman alpha BAO points here. They give you a measure of H of Z. You need to normalize H of Z by picking a value of the sound horizon. And then what you can do is you can use the supernovae data to extrapolate. You see, here I've just parameterized H of Z, so this is just some functional form to give you a variation of H with redshift with a number of adjustable parameters. So this is just a flexible expression, so you can match evolving dark energy models with this functional form. So the BAO data and the value of the sound horizon fix H of Z at these redshifts. This functional form will then give you the luminosity distance for supernovae, and then the supernovae data, in this case the Pantheon sample supernovae, allows you to extrapolate to low redshift. So that's what's done, and here are the results. And you see the inverse distance ladder gives you a low value of H0. This is, and this is independent of dark energy equation of state or whatever at low redshift. So the inverse distance ladder gives you a low value of H0, and it doesn't matter if you put the WMAP value for the sound horizon, you get very nearly the same results. So it's not so you can mix.
Can I interrupt you for a second?
Yeah.
I mean, how can you say that, the equation of a state doesn't matter? Because you're using a particular parametric form here, right? And yes, for this particular parametric form, yeah, this is what you get. But if I use another form for the expansion history or for the dark energy with different flexibility, then the results can be different.
Right. Well, how much flexibility do you want? Okay.
Well, I mean, of just a different form. I mean, if you can have a kink, like a sudden change, in the equation of a state, rather than have a polynomial form.
All right. Okay. So you see that it's fitting well here. Okay. It doesn't. What happens below here? The functional form. This functional form at redshifts less than 0.1 doesn't really matter very much. Okay. For the distance out of because.
Right. I mean, we can discuss that later. I'm not saying that at a very, very low redshift, but I'm saying that, using different ansatz for the dark energy can generally, the high redshift middle range, they can give different results. In fact, we have models we can discuss later that can result in different things.
Okay. I mean, the motivation for this was, that practically any set of parameters in WWA you can fit beautifully with this functional form. Okay, so but this does not have steps in it. Okay.
Yeah. Right. Yeah.
Okay. So I mean, if we go back to the Hubble tension, if you assume the WMAP value of the sound horizon and you combine with BAO and you assume the Land Cdn model, then you get a low value of H0. So it's not this low value of H0 is not a specifically Planck result. Okay. All right. So there are other ways of attacking this without using CMB data. So an example. So here's an approximate expression for the sound horizon. And so you can replace the Planck value of the sound horizon by using clustering, clustering and weak lensing, and primordial nucleosynthesis, and then that gives you the baryon to photon ratio. So that's irrespective of the CMB. And if you do this, I mean, it's not brilliantly precise, okay, but it gives you consistent answer with Planck. And the key concern that I would have with this is the fidelity of the dark energy survey weak lensing constraints, which are shown here. Okay, but that's independent. That's completely independent. The CMB gives you a low value. There have been proposals that you can maybe resolve this Hubble tension by introducing early dark energy, so a scalar field that just pops up before recombination. But this is under pressure now from large-scale structure data, full shape large-scale structure constraints on the galaxy power spectrum. And in this paper, they've done analysis, and with early dark energy, a model for early dark energy, and they get a low value of the Hubble constant, and constraints on the contribution of early dark energy to the total energy density of the universe. So in this paper by Oliver Philcox and co, they combine, so again, this is based on full shape analysis of the galaxy power spectrum. So what this does is, what full shape analysis does is it gives you a constraint on omega m, on the parameter combination omega m h, because the shape is sensitive to the redshift of matter and radiation equality. And they find from this analysis an H naught of 65 plus 3 minus 5.4. Again, not brilliantly precise, but not fitting very well with the Riesedal result. So, and this is completely independent of the sound horizon. So, the motivation for early dark energy was to lower the sound horizon. That doesn't work very well. And then this analysis is independent of the sound horizon. It doesn't fit very well with shoes. So I think that and this is why I've been very, very concerned about the data for the Hubble constant, because there is no, I mean, there's been this problem has been around now for about 5 years. There's a paper on the Hubble tension practically every week on AstroPH, and there is nothing compelling from the theoretical point of view that can resolve this tension. And so but at the same time, there's an awful lot of evidence that that Lambda CDM fits observations very well. So I worry about whether the distance ladder measurements themselves are accurate. So one of the arguments that people have made is that there's a similar discrepancy from strong gravitational lensing time delay measurements, and this has always worried me, because there's an exact degeneracy in strong gravitational lensing time delays, with mass modeling. So you can put a uniform mass sheet and just adjust. That will change H naught and leave magnifications and time delays unchanged. So that's always bothered me. And in this recent paper, they've analyzed strong gravitational lensing observations with more latitude in the mass modeling. And what they get is 67.4, plus or minus about 4 kilometers per second per megaparsec. This is with using spectroscopic data to constrain the models. I think that what one should take from this is not so much the central value, but the fact that the mass modeling gives you quite large errors. So I think that it's not reasonable to say that that strong gravitational lensing time delays give a very significant discrepancy with the CMB measurements of H0. Okay, so let's go to now the distance ladder. I imagine that most of you...
I mean, just since, this is kind of thing that we can ask questions before you go to the distance ladder. Again, I think the papers which you mentioned, I mean, such as the Phil Cox, Sherwin et al., I mean, they are model dependent, right? I mean, they are basically getting matter priors from the Pantone. I mean, so I don't expect to get anything otherwise. I mean, if we basically use Lambda CDM, there's no agreement, no disagreement here that, yeah, we may end up to the same thing, right? So, but if you just have DR12 alone and not having really, prior information on your model, then I really doubt one can get any measurements of the H0 with such precision, right? So if you assume a model, right, but if you don't assume a model, then I think things can become very much vague. Don't you agree with this?
Well, so for this, I mean, sorry, for this, the key thing is that it doesn't use the sound horizon. Okay.
Right, but sound horizon is not something that we can measure anyway, right? I mean, it is degenerate with the Hubble constant. So there have been activities, including my own team, that we try to measure H0RD because, they are practically anchored to each other. And it's not easy to separate them. Even again, in this paper by the Phil Cox et al., I mean, they have some assumptions on the early universe to get rid of the RD and then matter density priors from the supernova. So, I mean, I'm not saying that there is anything weird about this analysis, but I'm saying that, if we assume a particular model for the expansion and then trying to fit things, I would not be surprised to get these things, which is maybe different from the H0 direct measurement from the Cepheids and supernova done by the Reese.
Yeah, yeah. Look, I'm not disagreeing very much. I mean, what's going on here is that, if you have a model like early dark energy, which is a minority component that is changing the sound horizon, it doesn't do very much to the, to the dynamics of the model. Okay, so that's what basically what this analysis is saying. Okay, that you can have something, some physical effect, which is keeping the background the same, pretty much the same as Lambda CDM, okay, but changing the sound horizon, that will not work. Okay, that's what this is saying. Okay.
Well, that I agree that, having a, simple modification would not help, but I'm saying that it doesn't mean that H0 should be 65. It's based on this assumption that, yeah, I mean, we are, you know what I mean? I mean, we can interpret these results in different way.
Yeah, no, I agree. That everything is done in some sort of theoretical context. And so, it just changes the level at which you have to modify the theory. Okay.
Right. Thank you. Yeah.
Okay.
Sorry, can I step in and ask a different question?
Yeah.
So in a 2 slides back, you looked at H0 when you used the BO plus omega B constraints, BBN constraints.
Yes, this one here.
Yes. So in that equation for RD, you're making an assumption that the sound waves are propagating through the only universe there at the adiabatic sound speed.
That's right.
So if you had non-adiabatic pressure waves, I know these are heavily limited by the CMB, but if that wasn't the adiabatic sound speed, if it was slightly different, then you would have a slightly different R drag.
No, I agree with that. Yes.
It's just the trouble is that then the fluctuations would have this huge ISW component,
right,
and which is immediately ruled out by the CMB.
Yeah.
But again, there's a model assumption about that C squared that's going into that equation.
No, that's right. That's right. I think what we're, I mean, it's not surprising that we've had this exchange, and it's one of the reasons why there's a paper a week on resolving the Hubble tension. Okay, right. I want to turn to the distance ladder. Okay, and is there a possibility that there are errors, problems with the distance ladder measurements? Now, you had a talk by Adam, so he will have told you that what's done is that you have geometric distances to nearby objects. So in Milky Way parallaxes, the LMC has very accurate geometric distance measurement from detached eclipsing binaries. There are now 20 of these things. They're in beautiful agreement. And the physics is very simple. It's basically just black body. So we've got an accurate distance to the LMC, less accurate distance to M31, where there are only 2 detached eclipsing binaries. And then the Mesa galaxy, NGC 4258, where there are beautiful VLBI observations that constrain the dynamics of a nuclear accretion disk. So, from the kinematics of the accretion disk, you get an accurate geometric distance. So those are the calibrators. And so you look at Cepheids or some standard candle in these objects, and then you compare that to your standard candle in nearby objects that host type 1 supernovae. So this is done in the SHOES project by making HST observations of Cepheids. And then to get an H0, you need to match this on to more distant galaxies that are participating in the Hubble flow. These are very nearby objects, and so they're affected by the velocity field. And that's done through comparing with supernovae. So these galaxies are chosen to have type 1a supernovae, so the supernovae hosts, and then that's matched on to distant supernovae. So there are 3 chains. And to explain the to explain the Hubble tension, if it's a systematic effect, you need to have a magnitude offset from here to here of 0.2 magnitudes, okay? Which, for this type of analysis is a huge effect, okay? But this is what the data really look like, and this is what has bothered me all along. So this is from a paper I wrote in 2014, and this was based on Adam's, on the SHOES 2011 data. So these are residuals from the best fit period luminosity relation for all of the galaxies in the SHOES sample in 2011. The red points are points that are accepted in the analysis by Reset al. And you can see a large number of outliers. Okay. And sorry, this dog is annoying me again. Yvonne, can you control the dog, please? Okay. So so just look at this. Okay. This is, you see the errors on the individual measurements are really large. This is a scale of 2 magnitudes, 4 magnitudes. Okay, the blue points are outliers that are removed because they just don't fit the period luminosity relation. And what we're looking for to explain the Hubble tension is an offset about the distance between these two lines, about 0.2 magnitudes. So it's not implausible that that there is systematic lurking at that level. Here's why here's why the errors on individual magnitudes are so big. Okay, and that's because even with the HST, all of these Cepheids are blended with nearby images, and this just shows you a couple of what are called scenes. Okay, so this is the HST photometry, and then they fit a model of blended objects. Okay, and then remove it. The red is the Cepheids whose magnitude you want to estimate. Okay, this is the residual from the scene reconstruction, and so so you remove the fit, measure the magnitude, and so blending, your ability to deblend these images introduces these large errors per Cepheid. Okay, so crowded field photometry is really, really tricky. Now, in 2016, this is what the data looks like. And so this is the basic set of data that's been used for all of the shoes H0 measurements. The outliers were removed in the 2016 analysis, and don't appear in the published catalog. So there's no way I can check the outlier removal. But the basic point that the errors are very large. Errors on each Cepheid are very large. You can see, and so the concern with this is that you're relying on averaging a large number of Cepheids with poorly determined magnitudes to get the precision in H0. Okay. So does that work? So here are some other points of concern. So between 2011 and 2016, they went from 11 galaxies to 19 supernova host galaxies. The ones in common between those two samples, the HST images are the same, basically the same. So what I did was I compared the 2011 photometry with the 2016 photometry, Cepheid by Cepheid. They're the same images, just reprocessed. And this is what I found. So these are what are called Wiesenheit dereddened H-band magnitudes, and here are the colors. And quite consistently, quite consistently, the colors show a very large offset. Okay, which is a really strange result because in this deblending analysis, the effect of blending on colors you know, if you've got a bit of contamination from nearby objects, it tends to cancel in the colors, which is why the scatter here is quite small. But there's a big color offset, okay, of 0.14 magnitudes, which is unexplained, okay. Now the point about this is a direct comparison of photometry, is that the errors, the differences here, are way outside the error budgets of either the 2011 or the 2016 paper. And the net effect on the Hubble constant is about 2 kilometers per second, just coming from the analysis of the photometry. So I think that's something to be really concerned about. But then there are other issues. This shows the period luminosity relation for M31. Very, very well observed. Low scatter in this relation. And the slope is minus 3.3 plus or minus 0.03, so tightly determined slope. If you do a similar analysis for the LMC, you also get a slope of minus 3.3. So that's for a nearby object. But here's M101 from the Reese sample. Okay, so here the slope is shallow, and then this is quite characteristic of the Reese sample. So this has a slope of minus 2.97, and it differs by 4 sigma from this slope. Okay, so what's going on? And you can track this back to biases. So what this shows is the shift in distance modulus as you change the minimum period for the reset L galaxies. They're selected in the V band, and you see these guys here at short periods are fainter than these guys. So if you so you'll get a Malmquist type bias. If you go to the low periods, then you'll get a Malmquist type bias that you'll tend to see only the brighter ones at low periods, and that shifts, that makes the slope flatter. And that's what we see here, that you get a systematic shift in the distance modulus, okay, for pretty much all of the galaxies as you change the minimum period. And that's a selection bias. What they did was they threw out low period objects, but it's clear that they're still incomplete, okay? And that's why the slopes, that's why these slopes differ, okay? All right, so that's pretty fundamental. If you're using these things as standard candles, then the samples at low redshift on your distance anchors should have the same statistical properties as those in the supernova hosts. And again, that difference in slopes can account for about a 2 kilometer per second per megaparsec systematic shift. But it gets even worse because if we look at the distance anchors, and the whole thing is tied to the distance anchors, the whole, the value of H is totally dependent on matching to the distance anchors. Here's what happens. This is the geometric distance to the NMC determined from detached eclipsing binaries. This is the distance modulus. This is the distance modulus for NGC 4258 determined from the dynamics of the Masing disk. But it's a straightforward thing that I can compare the Reese Cepheid photometry in NGC 4258 with the photometry in the LMC and get a relative distance modulus just from the Cepheids, okay? And that should agree with the with these geometric distance moduli, okay? So if I do that, if I assume this one and determine the NGC 4258 distance modulus, that's shown here. So blue points are LMC, red points NGC 4258, then this is the distance modulus I get, and that's discrepant with the maser distance modulus by 3.5 sigma, okay? So that's a real problem, okay? If you've got a discrepancy in the anchors, then there's a real problem, okay? And so that's a shift of 0.18 magnitudes. And remember that to explain the entire Hubble tension, something in the region of 0.1 to 0.2 magnitudes is all you need. Okay, so here's what you get if you use NGC 4258 as a distance anchor for the H0, and then the LMC as a distance anchor. This is the slope, best fitting slope of the period luminosity relation. This shows you the slope from Andromeda. This is the Planck Land Cdn value of H0, and here's where the data lie, okay? And these, what you have to understand about these contours is that the Cepheid photometry for the supernova host galaxies is the same. It's exactly the same. So you might think that they're marginally compatible with each other, but most of the data is the same. And this difference is reflecting a difference in the calibrations, okay? So if we look at NGC 4258, then these are the posteriors for H0. Here's the Planck value, okay? And these are not, very discrepant with the Planck value. The red line, I've put a slope prior of minus 3.3, which gives you another shift to lower values of H0. Okay, so now what happens if you combine these two? Okay, so here's NGC 4258 as a distance anchor, whoops. And here is the LMC as a distance anchor. You combine them because the detached eclipsing binary distance has smaller error, then you get a value close to the LMC, and then you get a strong tension with the Planck value. But if you combine them, then this is the tension between the distance moduli of the LMC and NGC 4258. These distance anchors are not consistent with each other. Here's where the measurements, what the measurements tell you, okay? And here are the contours. I mean, if you combine the two, you're sharing the pain between the distance modulus of the LMC and NGC 4258, but you're discrepant at about 3 sigma, from the best fit values. So here are the possibilities. That it's just a statistical fluctuation, that one or more of the geometric distances is wrong, both of which are really bad news for the distance ladder. Some very peculiar population difference between the LMC and supernova hosts, or some sort of offset in the period luminosity relation that's related to the crowded photometry. And that's what I want to explore quickly since I'm running out of time. So I've termed this the Shoes degeneracy, and I'm going to model it as just a constant offset in the magnitudes. This is not meant to be a realistic model, but but this will give me an offset in the intercept of the period luminosity relation. The point is this, that if this is the same, if this shift is the same for all of the HST photometry, then it cancels if you use NGC 4258 as a distance anchor, in which case you'll get a reliable value of H. But it will not cancel if you use resolved calibrators, like the LMC Milky Way RM31. And that's the Shoes degeneracy. So that's shown here. This is the standard analysis that Adam and Rees will tell you of combining different distance anchors. but if there's an offset, this is what happens. All that happens if you add in LMC and Milky Way local resolved anchors is they give you the same value as the NGC 4258 anchor. Okay, and the statistics of the combination just constrains the offset. So you're completely degenerate with a common offset. And so here are the values that you get from that analysis. So somewhere between 0.1 and 0.15 magnitudes. And with that, you're consistent with the CMB value for H0.
George, sorry, can I ask, can you go back to that figure again with the overlapping contours? So is what's happening here that the resolved Cepheids are just statistically much more powerful than the 4258?
No, I mean, it's because in this model, I have this parameter, okay?
Yeah.
And it cancels. So the red contour here is the same as the red contour here. So it cancels if you use NGC 4258 as an anchor. But if you use the LMC or Milky Way or M31 or anything with resolved photometry, then that delta A doesn't cancel. And so all that happens is that you constrain delta A.
Okay, so it's a free parameter then.
It's like a free parameter.
Okay.
Yeah,
okay.
and so here are the values.
Thank you.
Okay, so this is another way of sort of saying, you know, what would I need as a systematic to resolve the Hubble tension? The answer is, you know, a delta A of 0.1 to 0.15. And so the question is, how can I test that? Okay, you've got a degeneracy between that delta A, okay, in the Shoes analysis. The answer is use something else. And so an obvious thing is to compare with the tip of the red giant branch. So this is from the Friedman et al. Paper where she and her collaborators got, you know, 69.8 plus or minus about 2 and a bit. And the impression that the entire community has had, as far as I can see, is that it's indeterminate. It's somewhere in between the CMB value and the Cepheid value. Okay, so you know, that's what I think. That's the way I think that the community has interpreted these results, and that is not correct. Okay, because if I look at galaxies that are in common between the Friedman and the Rees et al. Sample, then what you see, and they mention this themselves, that the over a wide range of distance moduli, okay, or distances, the Cepheid distance moduli and the tip of the red giant branch distance moduli are consistent with each other modulo an offset, okay, and that's shown here, okay. So it's not that there's a lot of scatter between these two measurements. They're basically consistent. Well, they are statistically consistent with each other, but they offset depending on what anchor you use. So if you use NGC 4258 as the anchor for the Cepheids, you have the red distance moduli. If you use the LMC anchor for the Cepheids, you have the blue points. And these are offset by 0.14 magnitudes, plus or minus 0.02, okay, which is 7 sigma, okay? So what this is actually saying, the tip of the red giant branch are calibrated with respect to the LMC, and they disagree with the Cepheids calibrated to the LMC by about 7 sigma, okay? And they're consistent with the calibration to NGC 4258. And you can see this. I can show that this is a calibration issue because here are the distance moduli. And this is tip of the red giant branch, calibrated to the LMC. And this line has an H0 of 70. So this is consistent with the Friedman value of 69. The error here doesn't include the error in the anchor, okay? And then the shoes data with NGC 4258 as an anchor, 72.2. And then shoes with LMC as an anchor, giving you 76, plus or minus 1.5. These are the same anchor, okay? And they're very, very discrepant, okay? So, what we have is a low value of H0 that differs from the shoes value of H0. The shoes team have argued that Friedman et al. Have got the calibration of the tip of the red giant branch wrong because of extinction. So they've wrote a paper, One et al. 2019. This is the extinction in I band, which is the band used to measure the tip of the red giant branch absolute magnitude. So they've done an analysis and determined an extinction of 0.1 magnitudes. This was countered with a detailed paper by the Friedman group, where they get an extinction of 0.16 or 0.17 magnitude, depending on whether they use a dwarf galaxy or the SMC as an intermediary. So these differ by about 0.06, 0.07 magnitudes. That's actually not enough to explain this discrepancy, but it's enough to move this up by about 2 kilometers per second if the One et al. Extinction is correct. So it doesn't resolve the discrepancy, but it brings it more into line. So the issue with tip of the red giant branch, the discrepancy between tip of the red giant branch and Reese, is what is the level of extinction of the LMC? And I think that doesn't actually resolve the problem, and it goes part way to resolving the problem. But there's something else that you can do. And so very recently, the Friedman group has published a calibration of the tip of the red giant branch in the Maser galaxy NGC 4258. And this is a very important test, because if they use the Maser distance, they get an absolute magnitude in the I band, which is what this F814W is, minus 4.051 magnitudes. Calibration using their calibration of the LMC, of tip of the red giant branch, say that LMC, is minus 4.054. So in perfect agreement, okay, compared to the 0.1 magnitude difference between the Cepheids, the Cepheid intercepts for these two calibrators. So, so the tip of the red giant branch shows no difference between the NGC 4258 and LMC anchors, but the Cepheid photometry does. So here are my conclusions, okay? I'm sorry to have gone a bit over time. The tip of the red giant branch and the Reese LMC calibrated Cepheids are inconsistent. Okay, so there's an error somewhere. The LMC and NGC 4258 geometric distances are inconsistent using the Cepheid distance scale, but they're consistent with the tip of the red giant branch distance scale. Whoops. If the Maser distance is correct, then the Cepheid H0 is compatible with Planck. And the Shoes method has a calibration degeneracy. And we can reconcile the tip of the red giant branch and Planck values with Shoes if the Cepheid period luminosity intercept is too bright by about 0.15 magnitudes. So that so if I had a discrepancy of 0.15 magnitudes, I solve 3 problems. I then get consistency with the Cepheids between 4258 and the LMC and the Milky Way. I get consistency with Planck and no Hubble tension, and I get consistency between the tip of the red giant branch distance scale and the LMC distance scale. Now, it should be possible to resolve these problems by focusing on independent calibrations. So that includes Gaia calibrations, Milky Way Cepheids, and tip of the red giant branch in galactic globular clusters. So the differences in the distance ladder measurements are caused by differences in the local calibration. And that's the key thing that you should take from this. These differences can be resolved with a few select observations on a short time scale. And so I don't think we need to wait another 100 years to resolve the Hubble tension. This problem will crack in the next year or two. Okay, so that's it. Thank you.
Thank you, George. Thanks. So we've already had a lot of questions, but if there's any questions, then in the chat.
So David, Stephen, I raised my hand, but maybe I can ask. Thank you so much for the great talk, particularly last week we had Adam. So, okay, I have one question. Okay, suppose that there is a discrepancy between NGC 4258 and LMC as the most used local anchors. 2 questions. Do you think we can find out another reasonable, very low local anchor that we can use to compare things? And the second, is it possible to introduce some unknown error here, or you know, systematics or whatever, that we can make these 2 measurements consistent with each other, assuming that, okay, we can add a kind of a nugget term, let's say, and then trying to see that, okay, what we get. Because in that sense, still the measurement of the Hubble constant would be above 72 or so, right? So which is still substantially higher than the 67 given by the Planck. I don't want to talk about the TRGBs because, you know, they have a different nature, but if you just focus on the actors of the supernova and the Cepheids, then so okay, even if we make them consistent, yes, maybe it's not 74, but it would be 72, right?
What if you take it? If you take NGC 4258?
No, I mean, I'm saying that we assume that these 2 should be consistent with each other, right? So maybe there is an underestimation of the errors. I mean, it's great what you have shown that, yes, there is a discrepancy, but if we assume that there is something, there's an underestimation of the error, so we should, you know, add another budget to the error to become consistent with each other. But then these 2 are 2 measurements of the same phenomena, which we should be able to combine them.
Well, look, okay. I mean, just wondering how to answer this. Or maybe if I told you what I make of this, okay? Let's go to this, okay? So this is what you get from NGC 4258, okay? And this is what you have. So the difference between the black and the red, or whether you put a slope prior on the Cepheid period luminosity relation, and you should put a slope prior, okay? The point of this is to show that there are, you know, there are a number of issues. You know, there's clearly some sort of bias in the Reset-Al sample, which is giving you a shallow slope for the period luminosity relation. So that's another systematic. I haven't even discussed, you know, making corrections for that, okay? So there are a number of things going on, okay? So, you know, this would be compatible with Planck, you know, with, you know, statistical, you know, within the statistical errors. I think the question, you know, what would I do? What can you do to actually test for systematics? So, and there are a number of things that you can do. So with NGC 4258, I think it's important to revisit the analysis, the maser analysis, okay, the geometric distance analysis, and because it's a complicated analysis, okay, and check whether there are any errors or assumptions that can actually shift the distance. So I do that. I think that's important. Then what you can do is, as it turns out with NGC 4258, the HST photometry is more crowded than other supernova host galaxies. So there are a lot of Cepheid measurements, but they're towards the center of the galaxy. What would be good, and what Adam and his group have decided to do, is to target fields in the outer parts of NGC 4258, and you get two benefits from that. One is that those fields are less crowded, and secondly that the metallicities in the outskirts are closer to the metallicities of the Large Magellanic Cloud. So it'll be very interesting to see what comes out of those measurements. Does the discrepancy, is the discrepancy the same, or do things get better? So I think there are observations that can be made to help disentangle all of this.
Okay, thank you.
Okay, thanks. Any other questions?
And can I have one more question if there is no? It is more kind of ideological question, George. I remember from a long ago that from the first Planck meeting 2013, you were warning that don't mix low H0 and then you get weird dark energy stuff and everything. But it looks like that you have a very special interest on lambda. Is there something that you like about it, or it is purely you just find this Cepheid supernova measurements not reasonable, or you have some special interest on cosmological constant?
Whoa. I'm not sure how to answer that.
Do you theoretically think there is something neat and beautiful about cosmological constant? Okay,
all right. So one thing that I've learned, okay, is that the universe is much cleverer than me, okay. So it doesn't really matter what I think, okay. I don't think that it'd be presumptuous to say that I have some sort of deep insight into the cosmological constant, but at the same time I'm worried about the fact that if you want a quintessence type model, you've still got to come up with an explanation for why lambda is 0. Or very, very, very tiny, okay? Even if you want, quintessence. And then one of the reasons that I've never really been, persuaded by or attracted by quintessence models is, that if you had some sort of dynamical dark energy, scalar field or whatever, then isn't it peculiar that the observations are constraining W to be so close to -1? We could have found -0.4 or something like that. Okay, so the tighter the constraints come, to W equals -1, the flatter the potentials, the more unnatural the model, etc., etc. So that's as far as my prejudices go. But I don't take any of that seriously because we're talking about very deep, difficult problems. Yeah. So they're just personal prejudices, but I wouldn't give them much weight.
Thanks so much.
Actually, sorry, George, can I ask a question?
Sure.
It's related to the miras and the megamasers. So basically, Adam's able to parade out these different determinations, right, which are not related to Cepheids. Do you understand what's going on there?
So this is really interesting. If you look at the miras, there's been analysis of by Adam's subset of Adam's own group, okay, of miras in NGC 4258, okay. The Mira distance modulus agrees with the Maser distance modulus using miras, okay. So that's, that just strengthens the case that there's a problem with the Cepheids, okay?
Yeah, that's fine. That's, I mean, so basically, but we still could have a high H0, like, I mean, something north of 70, right?
Well,
I mean, maybe with big errors, whatever. I mean,
yeah. I mean, look, the what I'm arguing is that I mean, if you use NGC 4258 as your the sole distance anchor, okay, then you get a higher value than Planck, but not by much, and it's not significant by much. There are clearly other systematics in the Cepheid data because the slopes that you get are wrong, okay? And so if you then put a slope constraint, you get even bigger overlap with Planck, okay? Now, I wouldn't advocate these things, I wouldn't say because of that, there is no Hubble tension. I'm raising these issues as reasons to worry, okay? But it's not as simple and straightforward, okay? But if you then combine NGC 4258 anchors with LMC and Milky Way Cepheids and so on, then you could get a misleading answer because they're already discrepant.
okay. Thanks.
Okay, thanks. Any more questions? Okay. Okay, I guess not then. So in that case, thank you very much, George, again. The good talk. Interesting. And yes, that's it. So thank you.
Right. Well, thanks a lot. Thank you.